Welcome, everybody, to the first AMS invited lecture of this session, this meeting, which is good to be back after many years. I am truly delighted to introduce a remarkable mathematician. Rekha Thomas is the Walker Family Endowed Professor of Mathematics at the University of Washington in Seattle. She has done truly influential research in the areas of optimization and applied algebraic geometry, and has received many recognitions for her work, including being an invited speaker at the 2018 International Congress of Mathematicians, and she's an AMS Fellow. She has written many books and mentored many students. She's a remarkable teacher, and as you are about to see, she's an inspiring speaker. Today, Rekha will talk to us about algebraic methods in computer vision. Please welcome Rekha Thomas.
Thanks, Jesus, and thanks everyone for being here. So my talk today is going to be about a very basic task in computer vision, which is the problem of reconstructing a three-dimensional scene from pictures of it in cameras. Okay. And as we will see, the existence of these reconstructions is a very old classical problem, probably even older than photography itself. And also, for the purposes of this talk, I want to keep the setup really simple. So we're just going to talk about the most basic type of camera, which is the pinhole camera. And I will just talk about reconstruction from two camera images. How do you advance this thing? Okay, there we go. Okay, so let me start by showing you a movie of a reconstruction, just so you see what it looks like. So this is a reconstruction of the city of Dubrovnik that was done by downloading pictures of the city from Flickr. So there were 4,619 images, and these little tetrahedra you see are where the cameras are. So these cameras were taken by tourists or other people. I mean, the pictures were taken by tourists, and they were uploaded on Flickr. They were downloaded, and then this point cloud of the city was reconstructed using some of the methods that I will talk about. So in this reconstruction, about 3.5 million points were reconstructed, and the movie is from a paper called Building Rome in a Day that was done by a team of vision people at the University of Washington in 2009. So the first author on this is Samir Agarwal. He's my very long-term collaborator on vision-related work, and he currently works at Google. Okay, so let me start with a little history of the pinhole camera. So the pinhole camera is known as the camera obscura in the literature, and this literally means a darkened room in Latin. So the name is due to Johannes Kepler from the 60s. And the principle is simply what you see in the picture. So if you have a very well-lit scene and you have a dark box with a hole in it, then the image of the scene gets projected onto the back wall. It's inverted and also laterally inverted. So it's vertically inverted and laterally inverted. And the principle of this object, this camera obscura, is very, very old. So you already see writings of this in the 4th century in both Chinese literature as well as in Greece. It appears again in the work of the Arab scientist, physicist Alhazen from about 1021. And during the Renaissance and post-Renaissance period, this camera obscura was used very extensively. So Da Vinci is credited with having actually constructed a physical model of the camera obscura. And it's also, there's this very controversial theory that this was a big tool in the work of painters like Vermeer. So this picture on the extreme right is one of the Vermeer paintings. And this one, for instance, is supposed to have been made with the camera obscura. So this is controversial. And up until maybe the end of the 1700s, this object was used mostly in astronomy to look at pictures of the sun. So like, for example, to see solar eclipses indirectly, for telling time, and also as an aid in drawings. Okay, so this is the basic pinhole camera. And here is an illustration of how the pinhole camera works in a modern photograph. So this is an image of the new royal palace at the Prague Castle, projected onto the attic wall through a hole in the tile roof. Okay, so this is an actual illustration of this inverted image that you see in the pinhole camera. Okay, so photography itself was born maybe at the beginning of the 1800s. So the originators of the whole thing is supposed to be Louis Daguerre and Henry Fox Talbot. So they figured out how to permanently capture the photograph by putting a chemically coated screen at the back of this camera obscura. And Daguerre was a set designer in the theater in Paris, and Fox Talbot was a scientist at Cambridge University. So both of them did this for the purposes of their work. And after that, so this is around 1936, so somewhere around there, the first three people mentioned here figured out how to capture the photograph. And then, the rest of it is a very brief history of photography. So in 1888, the Kodak camera was constructed by George Eastman. In the 1930s, the first single lens reflex camera was constructed. This is the fancy camera that we all had about 20 years ago. And then during World War II, Polaroid came around. And in 2000, the first phone camera came from the Japanese company J-Phone. Okay, so this is a very brief history of photography with a lot of other things that I have left out in between. Okay. So now let's come to the actual mathematical formulation of the pinhole camera that I'm going to use throughout this talk. Okay, so the pinhole camera has two parts. The first is the center of the camera, which is called C in this picture. It's located at the origin of the world. And then there is an image plane, which is the two-dimensional plane on which the picture is recorded. So this is placed in this particular configuration on perpendicular to the z-axis. And the distance from the center to this image plane is the focal length of the camera. So this is called little f in the literature. And the way you take a picture is, if I want to take a picture of this point Q, which is in the world, you draw a segment from Q to the center, and you look at the intersection of that segment on the image plane. So in this particular drawing, the image of the blue point Q, which is called the world point, is the red point X, which is on the image plane. Okay, so this gives us a map from R3 to R2. And if you can calculate it, so if the coordinates of the Q point is X, Y, Z, then the coordinates of the X point, let's assume it's located at Z equal to 1, is Fx over Z, comma, Fy over Z, where F is this focal length. Okay, so Q will always be my world point, and X will always be the image point. And the unfortunate feature of this map is that it's a rational map, which is not too bad, but there is actually a nice way to linearize it. So in Vision, what you do is you bump everything up into projective space by adding a fourth coordinate. So the world point now becomes X, Y, Z, 1, and then it gets mapped to the image point, which also has this 1 at the end. And because we're working in projective space, you can scale the image point by Z, and therefore you can rewrite the image as the product of this 3x4 matrix, which is called the camera matrix, times the input, which is the coordinates of the world point. Okay, so this is basically the pinhole camera map. It is a central projection from the world to the image coordinates. Okay, so some very basic terminology. So for the rest of this talk, we'll talk about the general projective camera. And by that, I just mean a map from P3 to P2. It's a rational map. It's a linear map. It just sends Q to A times Q. A is a 3x4 matrix of rank 3. Okay? Now, the rank 3 is important because if the rank is smaller than 3, then the world collapses onto a line or a point, which we don't want. We want the image to be on this two-dimensional camera plane, okay? The center of the camera is the unique projective element in the null space of the matrix. So this is a 3x4 matrix, so it has a one-dimensional kernel in Euclidean space, but a single point as a projective point. So that point is the center, and at that point, the image is not defined, which is why it's a rational map from P3 to P2. But otherwise, this is what it is. Okay? So this is the type of camera I'll talk about. This is the general projective camera. It generalizes the pinhole. Okay, so now let me come to the question of reconstruction. Okay, so what we would like to know is the following. Suppose I have 2 cameras, so I'm only talking about reconstruction from 2 cameras. Hopefully you'll see that that's already quite interesting and complicated. So if you have 2 camera images, which are shown in these 2 rectangular boxes, and let's say I'm given tuples of points. So I have xi's in one camera image and yi's in the other camera image. So I have these pairs xi, yi. We'll call them correspondences. So I have m of them, and they're paired up. So x1 is paired up with y1, x2 with y2, and so on. What we would like to know is, are these images of m points in the world under 2 projective cameras? So this is the existence question. So is there even a possibility to reconstruct these m point pairs as the images of some 3-dimensional scene, which would consist of m world points? Okay, so this is the existence question. It's a really classical question in some sense. So I want to show you an example of a related question that goes back to the French mathematician Charles. So this question was posed in 1855. It's called question 296. And it asks the following. If I give you 7 correspondences, xi, yi, and they're images of 7 world points, Q1 through Q7, in 2 projective cameras, he wanted to show that there exists at most 3 projective reconstructions up to P3 automorphisms. Okay? This was solved by Hesse in 1863. So the photography, as I said, came into being in the 1830s. But even before that, these questions were important, both because it was connected to projective geometry and also because there was photogrammetry even before photography, which was the science of constructing 3-dimensional models from, say, archaeological surveys and other types of maps that people used to take. Okay, this is a very classical question. Okay, so let's come back to projective reconstruction. So what we have are these images, xi, yi, or potential images, m of them. And if a reconstruction exists, then the task is to find the 2 cameras that took these pictures, as well as the world points Q1 through Qm that imaged to these xi's and yi's. Okay, so this is the reconstruction problem, assuming that the reconstruction exists. Okay, so because we have a projective camera, there is a slight caveat to what you can actually reconstruct. So if you think about it a little bit, if I take the product A times Q, then I can stick a 4x4 invertible matrix H in the middle of A and Q. So I can rewrite A times Q as AH times H inverse Q. That doesn't change the product. And this is possible for every H that is in PGL4. So general linear group, that's up to scale, 4x4 invertible matrices. So if I'm able to do a reconstruction from my image correspondences, then I can only do it up to a projective transformation. Okay, so this is another reason why this is called a projective reconstruction. It comes from a projective camera, but also the reconstruction is only possible up to a projective transformation. So here's a picture just to illustrate what this looks like. So here are 2 original images that you see on the top. And then below, you see 2 projective reconstructions of these 2 houses. So you see the projective transformation acting. And these pictures are from the classic book on this subject in computer vision by Hartley and Sisserman. And I'll put up the reference at the end. Okay, so we are looking for projective reconstructions, or in other words, that's the only thing that's actually possible. Okay, so now let's convert this reconstruction question let's rewrite it in a different way. So I have two cameras, as we saw. So in this picture, you see the two cameras as the two rectangular boxes. And then each one of them has a center. So the center of the first camera is C, and the center of the other camera is C prime. And let's say we're taking a picture of this world point Q. It images as X in the first camera and as Y in the second camera. Okay? So this means that I have the equality that AQ is X. A is the first camera. Q is the world point. So AQ is X, and A prime Q is Y. The tilde just means that we are looking at equality in projective space. Okay? So now let me rewrite this. So AQ is X is the same thing as saying that AQ is equal to some lambda X for some scalar lambda. And A prime Q is Y is the same as saying that A prime Q is equal to lambda prime Y for some scale lambda prime. So I can rewrite the first line in terms of the matrix equation that you see in the second line. And then that, if you think about it for a moment, is the same thing as saying that the determinant of the matrix is 0. So this matrix is a 6 by 6 matrix. So remember, A and A prime are 3 by 4 matrices. X is a column, and Y is a column. So altogether, the matrix is 6 by 6, and we're saying that there's something in its kernel. So I can rewrite this by eliminating Q and the lambdas as just determinant equal to 0. OK, so that, in turn, is a bilinear equation in X and Y. So we can rewrite that as, say, Y transpose Fx, where F is some matrix. And this is called the epipolar equation of two cameras. Okay? Let me rewrite it one more time. So this is also the same thing as writing X transpose Kronecker product Y transpose times the vector of F. So F is a 3 by 3 matrix. So the vec of F is just the 9-dimensional vector that you get by concatenating the columns of the matrix F. Okay? So this is the epipolar equation, either in the form Y transpose Fx equal to 0, or in the second form in terms of Kronecker products. Okay, so I am abusing notation a little bit in all these slides. So X and Y in the beginning were points in R2, but when you see them like this, they have been homogenized. So you should use, I'm using the same notation whether the point is in R2 or in P2. Okay, so this matrix F is really the essence of the two cameras. This is called the fundamental matrix of the two cameras. It's, as I said, a 3 by 3 matrix, but it's real. And much more importantly, it has rank exactly 2. Okay? So it's not just rank deficient. It has to have rank exactly 2. So now we have this epipolar equation we can solve given X and Y, look for the matrix F. And if there is an F that is real 3 by 3 of rank 2, then there is a reconstruction. And from the F, you can reconstruct the cameras. That is actually a very simple formula. OK, so this F is going to play an important role for the rest of the slides. Right, so now let's come to the projective reconstruction pipeline. So I again have my M correspondences, and the reconstruction exists if and only if what I said on the previous slide works. That means there must exist an F, 3 by 3, real, rank 2, and it must satisfy the epipolar equations for all M correspondences. Okay? So the previous slide, we saw one epipolar equation for one correspondence. Now I have M correspondences. So what I will do is I will pack these Kronecker product vectors into the rows of a matrix. Let's call it ZM. So this is now a M by 9 matrix. And I'm looking for something in its kernel, which will be the vectorization of F. If it has rank 2 and it's real, then we have a reconstruction. And then once you find F, the rest of the work is pretty easy. You find the cameras, you find the world points. I won't talk about that at all, but that work is fairly straightforward. Okay? So let's talk about the existence question again. So we're looking for the existence of such a 3 by 3 real matrix of rank 2. Okay. Now, here's the famous algorithm that vision people use to compute F. This is called the 7-point algorithm. It's one of the simplest of an entire class of problems that are called minimal problems in vision. If you want to hear more about this, there's a talk by Timothy Duff on Friday, where they're using machine learning to figure out F. But this version that I'm telling you is the most basic minimal problem that exists in the literature. OK, so the way you reconstruct F in practice, which is an algorithm that exists everywhere, it runs on your phones, for example, or at least a version of this runs on your phones. It's called the 7-point algorithm to find F. So what they do there is they take 7-point correspondences, and you'll see in a moment why, 7, and they solve the equations that you see on the left-hand side. So Z7 vec F is equal to 0, and look for F that's real, rank 2, and 3 by 3. OK, so this, the algorithm in the white box, it's not algebraic, right? Because we're looking for a matrix that is exactly rank 2, with not just rank at most 2. So the 7-point algorithm is the version where you relax the problem to its algebraic version. So what we now do is we look for something in the kernel of Z7. So Z7 vec F is equal to 0. So now let me say why you take 7 points. So if you have Z7, then we have a 7 by 9 matrix. Projectively, the kernel is a line. So it's a line in P8. So every 3 by 3 matrix is identified with a point in P8. And now, instead of solving for rank F equal to 2, we solve for determinant F equal to 0. So that's the closure. It's an algebraic problem now. And this is a cubic hypersurface in P8. Or it's actually a hypersurface in the space of 3 by 3 matrices. So I'm kind of identifying the two. OK, so now what we have is a cubic surface that's being intersected with a line in the space of 3 by 3 matrices. So we expect 3 solutions, and at least one of them is guaranteed to be real. OK, so the real part is not so difficult. But the problem is none of these matrices may be rank 2. So even though this is the generic pipeline for constructing these F matrices, it can often fail. It may not be that you can actually construct an F through this procedure. So we studied the existence problem some years ago, and in a paper with Samir Agarwal, Han-Long Lei, who was my student at the time, and Ben Strumpfels, we answered the existence question. So if M is less or equal to 5, then we prove that there is always an F, meaning there's always a real rank 2 matrix that lies in the kernel of this Z matrix. So here I'm looking at all possible M's. So any ZM you take, as long as M is less or equal to 5, there is 1. But for M equals 6, 7, 8, contrary to popular belief, this algorithm can fail. Okay? So there may be no rank 2 matrices. And the pictures you see at the bottom are examples of configurations for which there is no rank 2 matrix. OK, so this is the complete answer for the existence question. We don't have to worry about M bigger than 9 because the whole matrix is some K by 9. So the kernel will not, the question only makes sense for M at most 9. All right. So now let me move on slightly to a more ambitious type of reconstruction, which I will call a chiral reconstruction. Okay? And the question here is, can you make a 3D reconstruction of the same input that we had so that the reconstructed points lie actually in front of the cameras? And you might think, well, isn't that obvious? Don't they always have to be in front of the cameras? Yes. But projective reconstructions actually do not guarantee that. So remember, we're working in projective space where x is the same as minus x. So you can have reconstructions like this that are projective, but they're not chiral. So here's a picture of a comb, and on the other side, you see a projective reconstruction that has been split across the plane at infinity. And this is a perfectly valid projective reconstruction, but this is not the type of reconstruction we want. Okay? So there is some directionality that's important to cameras. Cameras are physical objects. They cannot see behind them. And you certainly cannot have a reconstruction that is split across the plane of the principal plane of the camera. Okay? So let's ask for a chiral reconstruction, which is now definitely a semi-algebraic question with inequalities. And let me stop for a moment and just point out why the projective reconstruction doesn't always provide a chiral reconstruction. So just coming back to the camera picture, we had the viewing plane, which was that square, the rectangle that you see there. But parallel to this viewing plane, there is another plane called the principal plane of the camera. So this is entirely parallel. It contains the center of the camera. It's the blue plane that you see in this picture. And if you want to be in front of the camera, you have to make sure that the line from Q to C is making an acute angle with the principal axis. So the principal axis is the Z-axis in this picture. So we need an acute angle between the two. And it's a little bit more complicated than that because we're working in projective space, but roughly speaking, what must be true is that your reconstruction, along with all the criteria for being projective, must also satisfy these inequalities that you see here, okay? So let me just unpack these inequalities for a moment. So remember, we're working with two cameras, so there are two principal axes. N1 and N2 are the directions of those principal axes. I'm just fixing one direction. And N infinity is the normal of the plane at infinity in P3, okay? So again, we're just fixing one normal. And then I need these three inequalities to be satisfied for every world point Qi, okay? So these inequalities, they look quadratic, but really what they're saying is that for every inequality, say the first one, it's just saying that the two dot products that you make have to have the same sign. So either they are both positive or they are both negative. So if you unpack that, then basically you get some sort of polyhedral condition that is given by the three planes that we are looking at. So there's the principal plane of camera 1, principal plane of camera 2, and the plane at infinity. Okay, so roughly you see a picture like the one you see on the extreme right in the bottom. We have to make sure that some signs are satisfied. Okay, so this is where chirality comes from, chiral for sign. And there's something called the chiral domain of cameras, which is the part of the world that the cameras can actually see. And we want to ensure that we are in that region when we do the reconstruction. Okay, so this is chiral reconstruction. And here are the results for chiral reconstruction. So this is quite a bit more complicated than projective reconstruction. And this is joint work with Andrew Pryhuber, who is another student of mine, and Samir's, and Rainer Zinn from the University of Leipzig in Germany. And we did this during the pandemic. So the results are as follows. So this time, if m is less or equal to 3, then there's always a chiral reconstruction. And then just jumping to the very last line, if m is greater or equal to 5, then a chiral reconstruction can fail. And this can fail even if the xi's and yi's are in general position. Okay, so m greater or equal to 5 is not good news. Of course, there might exist one, and there will exist one if your pictures are really pictures of a three-dimensional scene. But in general, if you just take point sets, 5 here and 5 there, then they may not be any real reconstruction of these point sets. The most interesting and complicated case is actually m equal 4. So for m equal 4, there are 6 combinatorial types in which the points can appear. So for example, the first picture has the 2 sets of 4 points in general position. The second picture has one side in general position. The other side has 3 points in a line, and so on. So there are 6 combinatorial types. And among these, all the ones with blue stars will have a chiral reconstruction, and the ones with the crosses do not. Okay? So this work it requires quite a bit of technical tools. Especially, we need to understand the subspaces that live inside the determinantal variety. And these have been studied classically. So we use a result due to Atkinson that we read about in a paper of Joe Harris and Eisenberg. And they tell you that these planes that live inside the determinantal variety, in our case, fall into 2 categories. Either they are something called compressed spaces, or they are subspaces of skew-symmetric matrices. And then you have to work with those, and it's at the end of the day, you get this result. Okay? So this is the story for chiral reconstruction. And I want to, in the next few slides, focus a little bit on the very last case, which is the m equal to 5 case. Okay? So for m equal to 5, it's going to fail, and then after that, it's going to fail for anything bigger because you can have sub-configurations that fail with m equal 5. Okay, so let me talk a little bit more about chiral reconstruction of 5 correspondences. And we'll see that a lot of classical algebraic geometry appears in this setting, okay? So I'm just focusing on 5-point correspondences. So I have this matrix Z5, which is now a 5×9 matrix. Its rows are these Kronecker products. So you can think of the rows as rank 1 matrices, if you like, that have been vectorized. The null space of Z5, which is this N of Z5, is a copy of P3. Right? So it's a 5×9 matrix. So in affine space, it has a null space that's 4-dimensional. In projective space, it's a P3. And if we wanted a projective reconstruction, then what we are looking for is a point F in the intersection of the null space with the determinantal variety. Now, that is a cubic surface because the null space is a P3 and the determinantal condition is a cubic polynomial. So this is a cubic surface like the one you see on the right, the red surface. And we need something that is both real inside this intersection as well as rank 2. Okay, so we're looking for a rank 2 F that lives on this cubic surface. And if you want the reconstruction to be chiral, then in addition, it has to satisfy inequalities. So I showed you one version of the inequalities in terms of these N's and Q's in a previous slide. But you can convert those inequalities into the language of the F matrices, and now you have fairly high degree, degree 6 polynomials that have to be satisfied. Okay. So it may be good to pause for a moment and realize that these are inequalities in projective space. So if they're satisfied by F, they also have to be satisfied by minus F. So it's really important that they are even degree. Okay? So these are degree 6 polynomials, and these are the versions of the chiral inequalities in this F space. So really, pictorially, what I'm trying to say is that if there is a reconstruction, there must be a point on this red cubic surface that is real and rank 2. The rank 2 part you'll see is not difficult. But more importantly, it has to satisfy these complicated inequalities that you can draw on this cubic surface. Okay? So this is basically what we're looking for. All right. So it turns out that in this example, there is a very, very elegant way of repackaging this requirement. And this is via via the lines on a cubic surface. So it is a classical result in algebraic geometry that every smooth cubic surface has 27 lines, 27 complex lines. Now, I'm going to produce for you 27 real lines that come from 2 cameras. Okay? So the first set of lines are like this. So you start with your xi's. There are 5 of them. And look at all the matrices that have xi as in its right kernel. Okay? So if you do the dimension counting, you will see that this is actually a line on this cubic surface. So let's say it's one of the red lines that you see there. And similarly for the yj's, you can look at all the matrices that have yj in its left kernel. Those are also lines. Okay? So they are the blue lines, and there are 10 such lines, okay, altogether. 5 lines from the xi's, 5 lines from the yi's. But now it turns out that these 10 lines secretly carry with them a 6th pair of lines. And you get them by just looking at the span of these Kronecker products, which are rank 1 matrices, if you like. So if I take the span of 5 rank 1 matrices, generically I have a P4. And this is intersecting P2 cross P2, which is the variety of rank 1 matrices in degree many points, because P2 cross P2 is a dimension 4 variety, and the plane is also dimension 4. They live in P8, so they have exactly complementary dimensions. And so they will intersect in degree many points, and the degree of P2 cross P2 is 6. So there are 6 points of intersection. 5 of them are the ones we already have, and there's a 6th one, which I will call X6 transpose Kronecker product Y6 transpose. Okay, so they secretly carry with them 2 more lines. And now the very nice fact is that if you take these sets of lines, the X lines and the Y lines, they form what's called a Schlafly Double Six on this cubic surface, okay? So what that means is you have a line configuration with 6 lines here and 6 lines there. The x lines are mutually skewed, so they don't pairwise intersect. The y lines are also mutually skewed. They don't pairwise intersect. But the xi line intersects the yj line if and only if I is not equal to j. So this is the definition of a Schlafly Double Six. It's a special line configuration that lives on cubic surfaces. So from 2 cameras in vision, you get a Schlafly Double Six on this cubic surface. Okay, then there are 15 more lines. So all of the lines I produced are real. So there were 12 real lines, and there are 15 more lines that come from tritangent planes. They're also real, okay? So this is a very special case of a smooth cubic surface with 27 real lines. It's a very special real topology that comes from vision, okay, from computer vision. Okay, so this is where we are. And now cubic surfaces historically have been studied as blow-ups. So this is a very classical result in algebraic geometry that if you have a cubic surface, a smooth one, then you can realize it as the blow-up of P2 in 6 points. And you can see the blow-ups here. So for example, the left plane is where the x's live. The right plane is where the y's live. And if you blow down the red lines, you will get the x points on the one side. If you blow down the blue lines, you get the y points on the other side. But more importantly, if you fix one plane, for example, say the left plane, then it turns out that the one set of lines, the red lines blow down to points, but the blue lines blow down to conics. So they blow down to conics that are leaving out 1 point at a time. Okay, so the points and conics are classically known, and now I have 2 sets of them. Okay, so remember when I'm looking for a chiral reconstruction, I'm looking for something on that cubic surface upstairs that satisfied those degree 6 polynomials. But now it turns out that satisfying those degree 6 polynomials is exactly the same as being in certain cells that are given by the line configuration. So I will skip the math exactly, but the chiral regions, you can see them upstairs on this cubic surface as certain cells that are bounded by the line configuration. And under the blowdown, they become cells that are bounded by the conics. So the gray areas that you see in the 2 pictures are exactly the places that allow you to make a chiral reconstruction. So there is this very nice picture if you're willing to work upstairs on this cubic surface where everything becomes really simple. Okay, so this is the case of 5 point correspondences. And now let me finish by just talking briefly about a different question, which is the question of the stability or the conditioning of this 7-point algorithm. Okay, so this, as I said, is a very common algorithm that's used everywhere, but only very recently have people started thinking about the stability of this algorithm or the conditioning of the algorithm. And to study conditioning, we need to understand the ill-post locus. So where is this problem not well-defined? And there are 2 ways in which it can be not well-defined. So remember, if you remember, there were 3 solutions to the 7-point algorithm. If they are distinct, it's fine, but it can be that the roots are repeated, or it can be that there are infinitely many solutions. And one way you can have infinitely many solutions is when the rank of this Z matrix, the ZK, is not the expected rank. The rank is less than K. And here's a result, a sample result for Z6. Again, we know the answer for all values, but for Z6, here is how the result will look. So the rank of Z6 is less than 6 if and only if there's a cubic surface S that arises as the blow-up of P2 at x1 through x6 and also y1 through y6, and their exceptional curves form a Schlafly Double Six. Okay? So again, classical algebraic geometry comes in. This is all happening under general position. If you want to hear more about conditioning, there's also recent work by Joe Khalil this afternoon. You can listen to that. It's about these algorithms, 7-point and 5-point algorithms. And so again, the cubic surface shows up. And I want to just reformulate this question one more time, and then I will finish. And you will see that this question can be reformulated in the language of classical invariant theory. Okay? So to do that, let me introduce a very classical form of a cubic surface that's called the Cremona hexahedral form. This is an explicit description of a cubic surface as the blow-up of 6 points. Okay, so normally there are ways to write down the cubic surface using determinantal representations, but you don't actually see the data of the points that you blow up. So if you look at this, formulation, you see that the first polynomial is a cubic, so that's the cubic part, but it's sitting in P5, and what the surface is actually in P3, so there are 2 linear equations that have to be satisfied in this P5. The first linear equation is, again, doesn't have any data in it, but the second linear equation you see has these coefficients, A bar, B bar, C bar, and so on, which is where the points come in, the points that you blew up. Okay, so what are these coefficients? So here is where classical invariant theory comes in. So remember, we're talking about points in P2. So the invariant theory of points in P2 under the action of PGL or SL is given by the determinants of, that you get by stacking 3 of the points in the columns of a 3x3 matrix. So the notation IJK means the determinant of PI, PJ, PK as the 3 columns. And on the right, I have another polynomial that I've written down that is a quadratic expression in these brackets. So these things are called brackets, the square brackets. And there is a definition of a particular type of polynomial in the brackets. And now here are 6 classical invariants of, there are 6 actually. 6 classical invariants of 6 points in P2, okay? So this, you can see, for example, in the book of Coble or in the articles of Coble from 1915. And these invariants have a lot of stories around them. They are related to what are called the Joubert invariants of 6 points in P1. And each one of these expressions you see is a number, right? Because each one of the each one of the summands in each line is one of these expressions that you see on the left upstairs. And they have a lot of symmetry and a lot of combinatorics going on, okay? So each little summand is called a syntheme, and the sum of all of them is called a pentad. They have a high degree of symmetry, and these are some invariants of 6 points in P2. And now here is the cubic surface theorem rewritten in this language, okay? So this theorem says that if you want to know whether the rank of Z6 is less than 6, then essentially you have to compute these 2 sets of invariants from the X points and the Y points, so you get a vector. And these 2 vectors become equal in projective space if and only if either the rank drops or there's a homography that relates the X's and the Y's together, okay? So this is a different way to package the same result and gives you some illustration of the types of mathematics that comes into these general questions. Okay, so let me end with some references. I didn't really give a lot of references at all. So the basic book to understand multiview geometry, which is the part of computer vision that I'm talking about, is this book of Hartley and Sisselman. It's freely available on the web. And there's a more algebraic book that's by Yi Ma and collaborators called An Invitation to 3D Vision. And in the last 10 years or so, there has been a lot of work that is trying to bring algebraic geometry and polynomial optimization into vision. And this area is broadly known as algebraic vision. A lot of people have worked in it. I have not had time to talk about the many, many projects that are going on here. But there's a very nice recent survey by Joe Khalil and Kathleen Cohn that you can find on the archive. It is a snapshot of basically everything that's been done in the last decade. So that would be a good place to look if you're interested. And thank you very much. These are all the collaborators that appeared in this particular talk. Thanks.
Thank you very much for the lovely lecture. If there are questions, there are 2 microphones in each side of the room. Just please feel free to come, approach the microphone. Thank you.
I apologize, I have these big lights in my face, so I can't quite see many of you.
Hey, Rekha. So, I had a quick question. You mentioned this conditioning theorem, so usually conditioning refers to sensitivity of roots under perturbation. I didn't see the sensitivity, so I guess once you have these invariants, then I guess you can sort of easily write out how much something perturbs once you perturb some of the invariants, I guess.
Yeah, so there's a lot more behind this. I just isolated this one little piece where you can get ill-posedness. So ideally, we want to understand, and Joe and collaborators have done some of this as well. So there's a whole, the actual conditioning work is Alperen and Samir, they're working on it. So this particular piece we isolated because it had all this rich mathematics in it that related it to classical algebraic geometry.
Right. So I guess the gist is that this particular set of coordinates is nice.
Yeah.
Okay. Thank you.
Thanks.
Any other question? So, Rekha, of course, if you take the pictures and you have your X's and your Y's from a real picture, let's say these are really coming from real cameras.
Right.
And you have the SAC data, you can reconstruct.
Yeah.
But what if there's noise? Is this so sensitive to that type of
Yeah,
thing?
absolutely. So in practice, there's always noise. And you don't do what I quite said. You have to do a maximum likelihood estimate. So there's some optimization involved. You would not be able to reconstruct exactly. So you instead reconstruct by minimizing distance to the actualized variety.
So yeah. I suppose in the very nice, at the beginning of your lecture, you had this very nice city reconstruction. So they also have so many pictures. So that helps, I guess, in the reconstruction. They have strategies for do that? Is there some nice mathematics there?
Yeah, so it's pretty much, so first of all, those pictures, those cameras are calibrated. So most cameras we use now are not projective. We know their focal length, right? So when you take a picture, it says at the bottom what the focal length is if you look at so those are calibrated pictures. So that's there are many styles of cameras, so that's a more complicated type of camera, so you have more information. And you have an analogous algorithm to the 7-point algorithm called the 5-point algorithm, which is, again, it can be solved. It's one of the big successes of Grosvenor basis theory in some sense. It's a minimal problem. And there, what you do is you reconstruct this matrix F, or the equivalent one, by using 5 points at a time. And then you basically keep the ones that are the best in terms of all of the data. So you don't try to get exact equality. You try to just minimize the norm of something. Okay, so there is a MLE calculation or optimization that has to happen at the bottom of it. So in practice, it's not such a idealized question. But these are, I'm talking about the case of perfect images. So if you have perfect images, you can reconstruct. But also, you can just ask this question mathematically. If you have two sets of points, can you reconstruct? So that is independently a useful question to know the answer to.
Any other questions, comments? If not, thank you so much again.